In this lesson, we are going to talk about differentiation. The result of the differentiation is called the derivative. The derivative of any function can be found using what we call the first principles. In the first principles, as we saw in the previous sections of this unit, is defined as f of x plus h minus f of x over h when h gets closer and closer to 0. So to find the derivative of any given function, we have to evaluate this expression and try to simplify it and find the limit. Hopefully the limit exists. Let us do a couple of examples. The first example says the function f of x is equal to x squared. We know that this represents a parabola with the vertex at 0, 0, and since the leading coefficient is plus 1, it opens upward, so it looks something like this one. The domain of this function is, as is apparent from the graph, is all the values of x in real numbers. So we can say the domain is x such that x is in R. The next part of the question says, use the first principles definition to determine the derivative of f of x is equal to x squared. And what is the derivative's domain? Again, to find the derivative, which we are going to call f prime of x, which is the same as delta f over delta x, we have to find f of x plus h, so x plus h squared, minus f of x, which is x squared, over h. Now, remember that the difference of a square, a squared minus b squared, is a plus b times a minus b. The numerator is the difference of squares, so I can write this one as x plus h minus x times x plus h plus x over h. Now, in the first bracket, x cancels out, so I get h times 2x plus h over h. And this one is the limit when h goes to 0. Now, this h cancels out with this h, so I'm going to end up with limit of h goes to 0 of 2x plus h. Now I can safely substitute h equal to 0, and I'm going to get this is equal to 2x. So we just found that the derivative of f of x equal to x squared is equal to 2x. Now the question is, what is the derivative's domain? You can see that the derivative is a linear function, so the domain is x such that x is in R. The next part of the question says, what do you notice about the nature of the derivative and describe the relationship between the function and its derivative? Remember that the function f of x was x squared, which is a function. The derivative of this function f prime of x is 2x, which is a linear function, which is also a function. So we can see that the function and its derivatives are functions, both of them. And also, the derivative can tell us the slope or the rate of change at any point. For instance, for the function y equal x squared, if we are asked to find the slope of the curve at x equal to 1, we are just going to substitute it back in the equation y equal 2x, which becomes 2. So the slope at x equal to 1 is equal to 2. So this equation simply gives us the slope of the function y equal x squared at any given value of x. The next question says use first principles to differentiate f of x is equal to x cubed. State the domain of the function and of its derivative. So we know that f is x cubed. So from here I know that f prime is the limit h goes to 0 of x plus h cubed minus x cubed over h, which is the limit of h goes to 0. Remember that x plus h cubed minus x cubed can be written as x minus a, so it's x plus h minus x times x plus h squared x to the power of 0 plus x plus h to the power of 1 x1 plus x plus h to the power of 0 x to the power of 2 close bracket divided by h. If I simplify this one, I get limit h goes to 0 of x minus x becomes 0, so I get h here times x exponent 0 is 1, so I get x plus h squared plus x times x plus h plus x squared, because x plus h exponent 0 is 1 divided by h. H cancels here. Now I can safely let h to go to 0. So x plus h squared becomes x squared plus x plus h is x times x is x squared plus x squared becomes 3x squared. State the domain of the function and of its derivative. If we look at the function, which is f equal to x cubed, the domain of f is x such that x in R. Now the domain of the derivative, d of f prime, is x such that x in R. Remember that the quadratic function is valid for x to be any real number. So that's the domain of the derivative of a function. Now we are supposed to graph the original function and the derivative. The red graph here is the original function, which is f equal to x cubed, and the blue graph is the derivative, which is 3x squared. You can see that the derivative is a parabola with the vertex at the origin. Both of them, they have a domain which is equal to real numbers. Now the question is to determine the following and interpret the results. The first one is f prime minus 2. Remember that f prime of x was 3x squared. So f prime of minus 2 is 3 times negative 2 squared, which is 4 times 3, which is 12. F prime 0 is 3 times 0 squared, which is 0. And f prime of 1 is 3 times 1 squared, which is 3. And to interpret the result, we can say that these numbers 12, 0, and 3 are just the slope at points negative 2, 0, and 1. The next question says, determine the equations of the tangent lines that correspond to the values we found in part C. The first one was x equal to negative 2. We know that when x is equal to negative 2, first of all, the function is x cubed. So the y value of this point is -2 cubed is -8. So we have to find the slope, the tangent to the curve at point -2 and 8. We know that the derivative is f prime is 3x squared. So when x is -2, the slope is m is equal to 3 times -2 squared, which is 12. So the line becomes y is equal to mx, which is 12x plus b. To find b, I know that it has to go through this point, so I'm going to sub it back in this equation. I get -8 is 12 times -2 plus b, which is equal to 24 negative plus b. Then I move -24 to the left, and I get b is 24 minus 8, which is 16. So the equation becomes y equal to 12x plus 16. The next point was point x equal to 0. So if x is 0, putting it back in this equation, we can see 0 cubed is 0, so we have to find the tangent at point 0, 0. We found that the slope at this point, 0, 0, f prime, is equal to 3 times 0 squared, which is 0. So our equation becomes mx, which is 0x, plus b, which becomes b. To find b, I put this one back in the equation, so I get 0 is equal to b. So the equation of the line here becomes y equal to 0. You may wonder y equal to 0 is just a point. It is not a point. Y equal to 0 is the x-axis. So x-axis is tangent to the curve at point x equal to 0. And the last one is the point x equal to 1. If x is 1, putting it back again in this equation, 1 cubed is 1, so the tangent has to go through the point 1, 1. And the slope at 1 is f prime 3x squared, which is 3. So the equation becomes y equal to 3x plus b. But since it goes through this point, I can say 1 is equal to 3 times 1 plus b. So b is equal to 1 minus 3, which is -2. So y is equal to 3x minus 2. We are going to introduce a new notation called Leibniz notation, which expresses the derivative in a different form. Before, remember, we said that the rate of change is delta y over delta x. We also said that when you find the limit of delta y over delta x, when h goes to 0, is defined as a y prime, which is derivative. We are going to define a new symbol, which is dy over dx. So it's just a new way of representing the derivatives, dy over dx. And if we want to evaluate the derivative as a point, let's say x equal to 0, we are going to write it as dy over dx, and then a vertical line, then x equal to 0. In the next example, we have a ball which is thrown in the air, and the function h of t represents the height of the ball at any moment. The height is in meters and the time is in seconds. We are supposed to find the rate of change of height of the ball at the time, and we have to use the new notation, Leibniz notation. So again, to find the rate of change, we have to find the derivative of h of t. So in Leibniz notation, we are going to write d of h to d of t is equal to limit of h goes to 0 of negative 4.9 t plus h squared plus 10 t plus h plus 1. This is h of t plus h minus h of t. So minus 4.9 is plus 4.9 t squared minus 10t minus 1 over h, and the limit has to go to 0. Now, if we expand the numerator, we get limit of h goes to 0, t plus h squared is t squared plus h squared plus 2th. So it's negative 4.9 t squared plus h squared plus 2th plus 10t plus 10h plus 1 plus 4.9 t squared minus 10t minus 1 over h. Now, if we expand the numerator, we get negative, we have to expand this one. We get negative 4.9 t squared with this 4.9 t squared, they're going to cancel each other. Then we are going to get negative 4.9 h squared, so it's the limit of h goes to 0 of negative 4.9 h squared. Then we are going to get negative 4.9 times 2th, which is negative 9.8 th. Then we have 10t here. With this 10t, they cancel each other. Then we get 10h, so plus 10h. And then we have 1 minus 1, they cancel, divided by h. Now you can see that h is common between numerator and denominator, so this h goes with this h, and with this exponent. So the answer becomes limit of h goes to 0 of negative 4.9h, negative 9.8t plus 10. When h goes to 0, we can safely replace h with 0, so this becomes 0, so the answer becomes negative 9.8t plus 10. The next part of the question says determine the rate of change of the height of the ball after 3 seconds. We found that the Leibniz notation of the height dh over dt, now we have to evaluate this one at t equal to 3 seconds. This is negative 9.8 t squared, which is 3 squared, plus 10. This gives us negative 19.4 meters per second. And the negative here tells us that the height is decreasing. The next example says differentiate the function y equal 1 over x, or find the derivative of the function y equal 1 over x. Express the derivative using Leibniz notation. So again, we are going to write dy over dx is equal to limit of h goes to 0 of f of x plus h, so 1 over x plus h, minus 1 over x divided by h. We are going to multiply the first fraction in the numerator by x, so I multiply this one by x and this one by x, and the second fraction by x plus h. So I multiply this by x plus h and x plus h. Now I can see that the two fractions in the numerator, they have the same denominator, so I can just subtract the numerator. So if I subtract the numerator, I get x minus 1 times x plus h gives me x plus h, and there is a negative here, so it's negative x minus h over x times x plus h over h. This is the same as x cancels out, so I get negative h over xh times x plus h. Now h is common between numerator and denominator. I forgot the limit here. H goes to 0, limit h goes to 0. This is the same as the limit h goes to 0 of negative 1 over x times x plus h. And now, since there is no h, which causes the denominator 0, I can safely let h to be 0, so I get dy to dx is equal to negative 1 over x times x becomes x squared. So this is the derivative of the function y equal 1 over x. The next part of the question says, using graphing calculator, graph the function and its derivative. If we use, for instance, Desmos, the red curve here is y equal 1 over x, and the blue curve is y equal, or y prime is equal to negative 2 over x squared, which is the derivative of the function. We can see that the function y equal 1 over x, the domain is the real number except x equal to 0, which is the y-axis, and the derivative is also x in real number except x cannot be equal to 0, again y-axis. One point that you have to remember is that the derivative of a function is not always defined. In the previous example, you saw that the function was like this one, and you can see that the function is not defined when x is equal to 0, because the function was 1 over x. That was f of x. Now the derivative of the function, which was f prime, which was negative 2 over x squared, has a graph which was like this one. And also the derivative was not defined at x equal to 0. This tells us that the discontinuous functions, they are not differentiable at points where there is a discontinuity. At x equal to 0 for this function, there was a discontinuity, and also at the derivative x equal to 0, it is discontinuous. Another point that you have to remember is that previously we said that if a function f of x is discontinuous at a point, the derivative is also discontinuous at that point. This doesn't mean that continuous functions are always differentiable at every point. Consider, for instance, graph A, which is this one. At point P, remember to find the slope at point P, we are going to find the slope of the secant, let's say PQ. Then we are going to decrement the value of h. Then we go to PQ here. So we start from this point Q, then we decrement h, we get to this point. We continue decrement h until we get to this line, which is tangent at point P. If we use this point Q and then we decrement our h value, we get to this point, and we continue decrementing, we are going to get to the same line which was horizontal, which is this line. So this tells us that the function is differentiable at point P. Now consider the next graph. Again, in this graph, we want to find the rate of change at point P. So I'm going to get a point Q here, and I'm going to start decrementing the h value. Doing this one, I'm going to end up finally to a point, let's say Q here, and this line represents the slope at point P. We are going from left toward point P. So this is a left limit for point P. If you look at the tangent line, you can see that the slope of this line is going to be a positive slope. Now let's find the limit from the right, going this way. I'm going to start with point Q here, and this red line represents my secant. If I decrement the value of h, I'm going to end up with this point Q and this line, green one, which is going to be tangent at point P. So this is the right limit of point P. But if you look at the green line is going to have a negative slope. And now comparing the two slopes, you can see that the left one and the right one, they are giving you different slopes here. This means that the function, which is represented by this graph, is not differentiable at point P, although the function that we started with was continuous. The next example is a piecewise function which is shown on the right, which is this graph here. The function is defined the following way. When x is less than or equal to 2, which is this part, it's given by this equation, y equal negative x plus 5. When x is greater than 2, which is this side of 2, the function is given by y equal 0.5 x plus 2. And we know that this point is 2 and 3. The question is that if we look at the graph, what is the slope as x approaches 2 from the left, meaning this way, and what is the slope if x approaches 2 from the right side? And what can we say about the derivative at point 2, x equal to 2? When we go from left to point 2, this is the line that we have to move on. If we find the slope of this line, we say, okay, the slope of the line is rise over run. If we get this point and this point, then the rise is 2, but the run is negative 2. So the slope or rate of change is 2 over negative 2, which is negative 1, which is correct because the line is falling. If we look at this line, meaning if we move toward 2 from the right, the slope of this line, if we pick 2 points, let's say this point and this point, the rise is 2 and the run is 4 positive. So the slope now becomes 2 over 4, which is 0.5. And you can see that the slope here, going from left and going from right, are different. So this means that there is no limit at x equal to 2, so the function is not differentiable at x equal to 2. So there is no value for derivative at x equal to 2. We could also find the slope using the equations. When we are moving from left toward 2, meaning this direction, this means that our x is always less than 2. So we have to use this equation because this is defined for x less than or equal to 2. So the slope of this line is equal to -1 because the coefficient of x is -1, which is correct. If we move from right toward 2, x is always greater than 2, so we have to use this equation, and the slope of the line here is 0.5, which is exactly what we got here. This is again another example of a continuous function which doesn't have a derivative at a given point, and the point here was x is equal to 2. The next question says, use the first principle's definition to prove that the derivative f prime of 2 does not exist. We know the function is defined as f of x is equal to -x plus 5, but for x less than or equal to 2, and 0.5 x plus 2 for x greater than 2. So, by definition, d of f of x to d of x is equal to f of x plus h, so negative x plus h plus 5 minus f of x, so it's going to be plus x minus 5 divided by h. And also for the second part is going to be 0.5 x plus h plus 2 minus 0.5 x minus 2 over h. Here x is less than or equal to 2, here x greater than 2. This is going to be simplified. If I distribute negative inside, I get negative x plus x, they cancel each other. 5 and -5, they cancel, so I get negative h over h, which is going to be -1. The next one, I distribute 0.5 inside, so 0.5x minus 0.5x gives me 0. 2 minus 2 gives me 0. And then I get 0.5h over h, which is going to be 0.5. For x less than or equal to 2, x greater than 2. And always limit of h goes to 0, limit of h goes to 0. Limit of h goes to 0, limit of h goes to 0. Since there is no h involved, the left limit to point 2, which is defined here, is -1, and the right limit to point 2 is 0.5. As it is apparent, the left and right limits do not exist, so the function is not differentiable at point 2. The next part of the question says, graph the slope of the tangent for each x on the function. How does this graph support your result in parts A and B? If we plot f prime, which is defined as -1 for x less than or equal to 2, and 0.5 for x greater than 2, we are going to get this graph. This is our x, this is our function f, 1, 2. Now, when x is less than or equal to 2, the derivative is -1. So if this is -1, when x is less than or equal to 2, so it's going to be a filled circle here, and this is going to be the first part, which is here. The second part says when x is greater than 2, the function is 0.5. So if this is 1.5 is here, so it's going to be a circle here, and then this is the graph. Now you can see that the function, which is f prime, is not continuous, because the easy way to explain it is that I have to lift the pen when I'm plotting the graph, or I can see that at point 2 the function is not going to have a limit, because the left and right limits, they are not going to be the same value. The left limit, which is this one, is going to be -1, and the right limit, which is this guy, is going to be 0.5.